This planet has a climate that is very special in comparison to other planets and maybe planets where extraterrestrial life could exist. And the usual problem is that if we sort of take our climate as the requirement for habitability, it's actually a very narrow range of the distances to the stars that would be.
Yes. On the the lights there. Just
as the distance of the stars. So if we just look at our sun, which of course has this is a unit of our sun, and if you look at the distance from the sun, we have our planets here: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and so on. And it's actually a very, very narrow band that covers Earth and maybe Venus and Mars, and that's it. If you go to the inner side here, you're so close to the star that you'll be locked by, as the moon is locked tightly to the Earth, that one side of the planet would face the sun. And this time locking is of the order of 1 billion years, which means that 1 billion years after accretion or so, this is what happens with Mercury. It will face the sun in one side and away from the sun on the other side, which means that it will be a very unpleasant place to live. On the other hand, we have Venus, Earth, and Mars being pretty close to the sun, or pretty much the same distance to the sun as each other. But the climates of these three planets are very, very different. Now, Venus has a very thick atmosphere, an atmosphere that's comparable to if we had evaporated all the oceans on the Earth. It's like you take 2 kilometers of ocean and you evaporate it into the atmosphere, and you have a pressure here of 200 atmospheres, which also makes the surface unpleasant from the pressure point of view, but that's probably not a big issue for life. You know, there's life in the deep ocean as well.
No, but I think it's a bit technical. It's also Venus surface of the place. So there's a place for the light to be floating in the atmosphere and more pleasant temperature and pressure.
Yeah. I mean, what you would need there, I don't know if anybody proposed that. Yeah. Anybody taking that seriously, that there should be life in Venus?
No, but it could be.
It could be.
Like in Jupiter's atmosphere.
Yeah.
Filters.
Of course, what you need, of course, would be availability of nutrients and things like that. There we have the surface ocean to compare with, but on the other hand, the atmosphere and the land masses provides for nutrients and things like that to the ocean. So, I guess that situation would be very different for Venus. Of course, not possible. But from sort of my perspective here, the big problem with Venus is, and of course maybe not that high in the atmosphere, is that it has a very high temperature.
Well, it's still the case that the outer level is pleasant in many ways, except that it's acid.
So in that sense, yes, sure. This is for what I will explain later, a sort of runaway greenhouse planet. And if you go to the other side, Mars, liquid water is probably frozen out and is in the planet now. It has a very thin atmosphere, and so it's sort of a deep freeze planet. So we have a narrow range here. Now, one puzzle in that connection is that the solar luminosity has not been the same all the time. If you look at the long time scale of the Earth, 4 billion years, we probably had a luminosity comparable of being down here in this luminosity-wise. Of course not mass-wise of the sun, and Earth might have been outside the habitable zone. So something on Earth has made it habitable on its own. Okay. And this something has to do with the greenhouse effect. So the common idea is that we start looking here, going back in time to 4.6 billion years, the solar luminosity has been increasing, and if you go back just 1.5 billion ago, the surface temperature would be below freezing point water. Now that might be a problem for life, but it might have overcome that, but it's also a problem for the geological record, because we know that that's not the case.
Yes, sir.
We know, yeah, I will return to that, but we do also know that going back in time here, this is like in this process, you never get where you think. I like that. Sorry about that. No, that's very good. That's very good. We know that back in time we've had liquid water. So something has heated the atmosphere to above this level, and this something you think is an increased amount of greenhouse gases.
I seem to remember that there's this habitable zone and there's this continuous habitable zone.
Yes.
So the continuous habitable zone is the one that takes the change in luminosity of the sun into account. What I remember, you said the Earth always has been continuous habitable zone.
With Earth?
That's not true.
Well, I think the short story is, or what I will try to convince you is that's not really so important, because the planet itself is able to react to the fact that the luminosity is changing. So in that sense, we are about, so the continuously habitable zone would be an even narrower band here, because the luminosity of the sun is changing. Okay, so this is the idea that greenhouse gases, and I will explain in a very simple model how it comes about with the greenhouse gases, that the atmospheric content of greenhouse gases has been much higher, and especially carbon dioxide, and it's now also discussed that maybe methane has a role to play in this. And that level here could be set by the following geological timescale balance, namely the outgassing from volcanoes, which is sort of purely geochemistry of a planet like ours, and we have volcanoes on Mars, we have volcanoes on Venus, so we have this outgassing of CO2. But then we have another factor on the surface, on the land surface of the Earth, which is this process called weathering, which is the following, that the CO2, part of the CO2 will come down to the surface as carbonic acid rain, and on the surface it will react with the exposed rocks here, calcium silicate rocks that will be exposed to the water and the carbon dioxide, and there will be an exchange between the carbon, actually the CO2 and the calcium, and you get some different types of rocks, and in that way you pull out CO2 from the Earth. Of course, when you have a source and a sink, there will be some sort of balance setting in for that. And the idea is that this balance might be what could bring this temperature above freezing here. So the key factor to the climate of the planet for habitability is really the chemistry of the atmosphere. This is sort of the starting point, going back to the 60s. You probably all know the story of NASA asking James Lovelock what to look for on Mars back in the 60s in order to look for life. And what he came up with was this observation, which could be made even in those days from Earth, then if you look at the chemical composition of the planetary atmospheres of Venus and Mars and Earth, Earth is very different from Venus and Mars. Even though climate of Earth is somewhere between these two. It's different in the sense that both Mars and Venus contains a lot of carbon dioxide. Carbon dioxide is dominating gas of the atmosphere. And the reason Mars is not warm is that the atmosphere is actually very, very thin. It's only 100 of an atmosphere at the surface of Mars. Okay? And the other factor is that oxygen is strongly present on Earth. There's very little carbon dioxide, but a lot of oxygen on Earth. And this here is the special case. These two are sort of the normal cases. This is the special case. And it's special in the sense that if it was left alone, on the planet, the oxygen would disappear completely by oxidizing surface and oxidizing all the gases and so on, and carbon dioxide would be sort of dominating. So the point there was that Earth's atmosphere, from a chemical equilibrium point of view, is far from equilibrium, and we all know that this is due to life. That life on Earth makes the atmosphere oxy and very low on carbon dioxide. And since the carbon dioxide is a greenhouse gas, there might be a coupling between the climate of Earth and biology. This was sort of put up as a whole called a parabola of sort of turmoil of how this works. This is the turmoil of Daisy World. I will not go into the details of Daisy World, but Walter Lovelock came up with this idea that you could imagine you had a planet covered by two types of daisies. You had the black daisies and the white daisies. And the black daisies would absorb all the sunlight coming down, while the white daisies would reflect all the sunlight that comes down. Okay. Now, the point is that these species here would depend on temperature. They would like to live at a specific temperature. Now, the black daisies like it cold, while the blondines like it hot, and the brunettes like it cold. This is sort of put into the model. So what happens is that the black daisies making the planet warmer, because it absorbs here, would then cease to grow and exist because it gets too hot. And on the other hand, if temperature just for a moment, think of this as a temperature axis. It's just this solar luminosity proportional to temperature. While if it gets warmer, the white daisies, which are slightly warm, they grow, and on the other hand, they then start reflecting the sunlight and cool the planet. So if we look at this as a function of the solar luminosity, imagine this growing with time. At the point where these species start growing, they will sort of have at low luminosity here. These black daisies would come up here, and that would result in heating the atmosphere because of a larger absorption. So this absorption is larger than the absorption of the bare ground. Okay, so it heats. And as the temperature increases, the luminosity increases here, you would have less and less black daisies and more white daisies, and in that way you would experience here a plateau of constant, more or less constant temperature here. So this is sort of an expansion of the continuously habitable zone, because in the time interval that is comparable with solar luminosity between 1.6 and 1.2 or something like that, which covers the whole history of the Earth, the surface temperature would be pretty constant. It was sort of the idea of this model. This is, of course, a completely unrealistic model of anything life, but the sort of set off a mindset of how to think about these things. So let me just, I don't remember the answer, maybe I should just wait. Let me just wait a little bit. Let me just, let me just now explain to you sort of the model that we use. The kind of model that would explain the temperature here. So first of all, the simplest climate model you could think of is just a model in which you look at Earth or the planet as one entity, sun here, radiating, and the planet is then cooling to space like that. So in this case, we have a cold space, 3 Kelvin. We have the planet somewhere in between, maybe 300 Kelvin. This is what we want to calculate, and of course we have the sun, which is 5 times. Okay. So this is a radiation balance between the sun and the cold space. Okay. So we imagine this system here to have a capacity of heat, and the temperature, which would be some sort of mean temperature of this one here. Let's just take this to be, in this case, the surface temperature of the planet here. This would, of course, depend on the incoming radiation and the outgoing radiation. Okay? So if incoming radiation is larger than outgoing radiation, the temperature would increase, and if the outgoing is larger than the incoming, the temperature would decrease. This is sort of the first climate model in order to explain, or sort of the most naive climate model we think of this term. So how would we then describe these two terms? Incoming here, well, it's just the solar radiation here, which we for present day calculation we take as a constant, but this is really what's changing from 0.7 to 1 during Earth history. But we only gain a part of the sunlight because sun is reflected. One part here, some fraction between 0 and 1 is just reflected back to space. This is actually what's happening on Venus now. Venus is a very bright planet, which means that it's not nearly as heated as one should think being close to the sun, because the reflection from Venus is much more due to the thick atmosphere. I think it's actually gaining the same order as Earth, even though it's closer to the sun. So this is the factor here, reflectivity. It's got a name, albedo. And this albedo, of course, depends on temperature of the it would depend on if it's a cloud-covered planet, how much ice would be on the planet, especially so. This is a factor we don't know quite yet, but it's a function of temperature itself. Okay. Now the outgoing radiation here, well, this is just the black body radiation, which would be some Boltzmann factor times the black body radiation, but not really the temperature here at the surface, because we have the greenhouse effect. If I have the surface here with the temperature, look up through the atmosphere here, then I know that the atmosphere, if I look at the atmosphere from above, I'm sitting up here looking into that, I cannot see all the way to the surface in the wavelength that is radiating. I maybe see down here one obstacle depth, and this is really the radiation I get. So I get something that is comparable to an effective temperature of the atmosphere, which might be different from this temperature. That's an effective temperature. Yeah. Let me just very shortly explain to you this greenhouse effect. The greenhouse effect, which could go both ways, but which is positive on Earth, depends on the fact that most sunlight is indivisible, what then just visible. So the luminosity of, of course they're not legal anymore, the light bulb. I don't have to call it an old-fashioned light bulb. Radiates around the luminosity of the sun. And there's very little absorption in the atmosphere at that wavelength. So visible light goes all the way to the surface. Which means, of course, that exactly the wavelength that we look is where the atmosphere is most transparent. That's, of course, natural. Our eyes are adapted to the atmosphere. This is, of course, where we want to look, where we can see the light from far away. So, the atmosphere is heated from below. You heat the surface here, and it radiates out in the long wave here. But the atmosphere is opaque in the long wave due to the greenhouse gases. Which means, of course, that we get an equilibrium here, and only when we get to a level of one optical depth from the top of the atmosphere, we get the release of the greenhouse effect. Now, how does that work? Now, with the greenhouse effect? Well, let's just mark in this one a temperature scale. Now, there's some temperature profile going up through the atmosphere. And you all know that it gets colder about a degree per 100 meters. Okay, so we have a decreasing temperature with height. This is height up through the atmosphere. And at some point we have the tropopause, and actually the stratosphere goes the other way. This is due to the fact that up here we have ozone that absorbs this one as well. Let's just look at the troposphere part here. Okay. Now, if I put in more, so basically what I say here, now if the optical depth is here, this is really the temperature I have. So this is my T effective temperature here, and this is my surface temperature T. So when I talk about the greenhouse effect, this is the delta T, which is the greenhouse effect. Okay? If I put in more greenhouse gas here, what happens is that I lift the level of radiation, because it becomes more opaque. Now this is the temperature here. Now, of course, I know that this effective temperature here should balance, this one here should balance that one. The temperature is not to change. So I lift this temperature here to this level. When I do that, and say nothing else changes, I'm lifting the whole temperature profile, and I get a larger surface temperature here. So this is sort of the anthropogenic greenhouse warming if you want, as a function of adding more CO2. So this is sort of the whole idea. Okay. So this one here, I can really parameterize in many ways, but I could write this as sigma, some greenhouse factor as a function of temperature, and then times my surface temperature, say 4 or 3, whatever I want. The message is that this one here has a factor depending on temperature, which is the greenhouse effect. So now I can start doing my model. So now I really have a nonlinear model and two nonlinear terms here as a function of temperature. And how will it look? It will look like the following. We're going to do it's obviously to Denmark. Okay, let me just plot as a function of temperature my radiation here. Okay. Now, first of all, the incoming here depends on this albedo factor here. This albedo factor here depends on the amount of ice I have on the planet. The more ice, the more it reflects. Okay? So at some point, at some low temperature, the planet might be ice covered, and it will sort of reflect as much as it can, and the incoming radiation will be some constant level below some C1 here. Okay. The opposite extreme, of course, if I have a very high temperature, I might have a planet in which all the ice is melted, okay, which means that increasing the temperature doesn't really change the albedo of the planet, and I have some other higher level of incoming radiation. Okay? So here the albedo is high, the albedo is low, and so it comes to the minus there. And what do? I'll just, somewhere in between, I can just, for simplicity, make just a linear connection there. The outgoing is just some increasing curve in temperature. It might be complicated depending on a lot of things, but let's just draw it as an increasing. So this is the incoming, and this is the outgoing here. Okay. Now you see that I find 3 steady states. So this should be more. But these steady states, these two terms, they balance, and this one from 0. Let's just look at the first point here. In this case, if the temperature goes below this level here, okay, the incoming radiation is larger than the outgoing radiation, which means that I get heating. So heat here, and on the other side it's on the contrary. Now here, if I'm below this point here, the incoming radiation is larger than the outgoing, so I have an increase here, and here I have a decrease, so I find 2 stable states here and an unstable state here. Right? So, you big physicists, I can just write this here as a minus. So, potential, like in the usual sense. Of course, this is then just the difference here, and you get this kind of potential out here to have it there, here, the minimum, good, there you have a maximum, and there you have a minimum, right? So we have these 2 stable states and an unstable state there. This kind of potential. This was sort of the first attempt at a non-linear climate model. And this is sort of the workhorse that one would use for these kind of studies. Now you could imagine that the amount of greenhouse gas is changed. The amount of greenhouse gas is changed by biology, a little bit like this one. This is of course the kind of model that goes into exactly this calculation. Let's say that I decrease the greenhouse gas content. What does that mean? If I decrease the greenhouse gas content, I can more effectively radiate. Right? So for a given temperature at the surface, I get more outgoing radiation. So this amounts to just raising this level here. So I can just move this level up here, like that, and you see what happens while I do that is that these 2 states, they merge, and here I have a bifurcation point. So I have a 7-node bifurcation at exactly that point. Okay? And on the contrary, if I increase the greenhouse gases, I would get down here, and I have a 7-node bifurcation at that point. And what I can plot here as a function of say I mean let's just say that what I'm calling here is mu times R0 as a function of my control parameter. Mu here, what I get here is really a hysteresis, let's see, depending on the sign of mu. What do I want? Let's say I want something like this. This is actually how it goes. Here is this is temperature here. This is this bifurcation point at the low temperature, and this is the bifurcation point at the high temperature, and I can get a hysteresis on my head. Okay? So suddenly I would get a jump in a model like that. Now this was first proposed in the 60s as a model of ice ages, and which is not for a pretty obvious reason, which is that you know that during ice ages the planet was never completely ice covered. So I mean this was proposed independently by sellers in the United States and particularly in Russia, in which these curves were established using that time, you know, I think they had started doing satellite measurements already then, so on and so forth. And of course, in our interpretation, we would be in this state, and we would maybe, a few, whatever number of years they had measurements, might be a little bit around this point here, and so in a sense, it was an extreme extrapolation of data that we got at that time. But the obvious criticism against this as being an ice age theory is, of course, that the mechanism for getting this lower point is, of course, that we saturate with ice, we cover the whole planet with ice. That didn't happen in the time. So obviously, this is not a model of ice age. Now, the ironic thing is, to return to your first question, is that just 10 years, 8 years ago, Paul Hoffman came with these disturbing observations of marines everywhere on the planet, even in the equatorial regions at times which were much further back in time, 700 million years ago. And these were global glaciations of snowball Earth. So this is really not a model of ice ages, but a model of snowball Earth. Okay, and it seems to cover this pretty much. And now we have sort of a beginning understanding of how we could really get out of the snowball Earth in a scenario like this, even though we have problems. So,
the reduction of the water vapor in the atmosphere is not enough.
To make
as the down partially.
No, it's not. The thing is, the tropical regions, half of the surface of the Earth is below 30 degrees. 30 degrees. It's just geometry. So you really need your ice to hit 30 degrees. And if you hit 30 degrees, it starts to go quickly. Because what happens there is, of course, that your latitudes will be more and more perpendicular to the sun. Which means, of course, that you get much more pay for your buck when you increase the ice perpendicular to the sun than if you do it up here when the sun radiates from into the equator. Right? So the tipping point is ice around 30 degrees. Latitude, yeah. 30 degrees latitude. Okay, so why couldn't it happen now? This snowball Earth. That is the theory is that I mean the reason that the snowball Earth that you could get into this was that you needed the carbon dioxide to. Let me see how to go out. Actually, it's been. Well, I won't tell you this because it's just been proven wrong, and that's sort of not the direction that I want to go into. Okay, let's then go back in time and see how this has really been with the gases, the atmospheric gases here, and reconstructions, geological reconstructions going back all the way in time, has more or less established this picture that the planet started out looking pretty much like the atmosphere like Venus and Mars, dominated by carbon dioxide. And it would be outgassing hydrogen, which on Mars escapes into space. But the theory goes that, this is sort of spoke by Carsten and others, that at some point the first life forms that really did something new were methanogenic life forms eating hydrogen. So you eat hydrogen and H2 plus CO2, and you produce this one here, two of these ones, plus another two. Okay? So we use the energy of the hydrogen, and hydrogen stays on the planet, doesn't escape to space because it will be bound in the methane. So methane would be increasing, eating the carbon dioxide. Okay. Now, when this happens, the greenhouse warming is being taken care of by the methane, because methane is actually a much more efficient greenhouse gas than carbon dioxide. At some point, photosynthesis is invented here. Now there are big discussions if this is really where it happened, or if this is where it happened, or whatever happened. But what we know is that at some point, about 2.4 billion years, oxygen level of the atmosphere rose dramatically, very quickly. And that is built on observations that right here some rocks are formed that could not be formed in an oxidic environment, and right here they're oxidic. So you can sort of see a layer, and just below no oxygen, and just above a lot of oxygen. Now, how can it be that it only increased there when oxygen started to be produced there? Photosynthesis. And there the idea is that oxygen, of course, is readily eaten by all kinds of processes. For instance, we can burn this guy, right? Methane and oxygen we can burn to carbon dioxide and water. We squeeze, of course, the carbon dioxide, we squeeze a little bit again. And it's also eaten by oxidizing the surface. We have the upwelling of reductants in the surface layer. We have bonded iron formation. Banded iron formation. There are observations of I guess that's rust layers taking out the oxygen. So first, the message, and at some point, of course, the surface is fully oxidized, and this rapidly increases, killing off these guys, or at least putting them off to anaerobic places, and life has sort of gone its victorious expansion over the Earth, and at some point it even took another jump here, which I guess comes from the fact that why did that happen? That happened maybe because when this level got up here, we invented more efficient photosynthesis, because we produce more oxygen. And this is really where life forms that we know, the Cambrian started. So we needed an oxygen level larger than somewhere in between here in order to get multicellular life, because we need a more efficient way of getting the oxygen transported into the metabolic activity of life forms. Right? And exactly these points, maybe you cannot see it, but there are dashed lines. There's one here and two here. These are the snowball Earth spells seen on Earth. It seems that snowball Earth here are really connected with the atmospheric content of these different gases and of the intervention of biology, because these really depend on biology. So if you want to simply try to incorporate some of it, you always have the problem of where to start and where not. And when you discuss these things with biologists, you come up with hundreds of processes. This is sort of just one scheme published by these biologists here of how do you see feedbacks in the climate system. Feedbacks in these kind of models are really factors like for instance the outgoing, the incoming radiations depends on the ice. This is a positive feedback, because what you have here is that if it's cold, you get more ice. You get more ice, you reflect more. If you reflect more, it gets cold, and you get more ice, and so on. And this is a positive feedback. Of course, there are all kinds of feedback. And then you can, of course, put up all kinds of different things, like the temperature of the leaf in the plant, the size of the leaf, the size of the canopy of the forest, the stomatal density, that has to do with lymph cells on the bottom of the leaves, and the atmospheric content of carbon dioxide. Now, if that's large, you have smaller lymph cells because you don't want to evaporate too much water, and if you're smaller, then it means that you get a larger temperature of the leaf because you're not cooling by evaporation, and that means you get a smaller leaf size, and blah blah blah. And there, of course, you can look at all kinds of feedbacks there. The problem with these things is that they are very hard to quantify. Right? As a biologist, you can publish these kind of things and say this and that happens, but when you're a physicist, there's no way, because how on earth can I see, is this loop really a loop that has any significance in comparison to, whatever other type of loops around this diagram? So what you really need is to make a model that will dynamically look at everything. So the most simple thing to think of, of course, a model like this. Let's just put this one up here. Now, as I explained before, the way biology goes in is through the amount of greenhouse gases that's put into the atmosphere. Okay? So the idea is, of course, the following: that life likes specific temperature. Okay? Now, life eats carbon dioxide and emits oxygen, which means that life would be cooling the planet. Because when you take out carbon dioxide, it cools. So let's effect from that. Now, if it gets too cold, life will cease to exist as much as before. So somehow life likes an optimum temperature. So what we want to see is how can that reflect back into this one here. So the simplest model you could think of is, of course, this is just writing out a way of having this greenhouse temperature to depend on the amount of carbon dioxide. So this Tg, it's really the difference here between, it should really be the effective temperature there, and since this is the temperature which governs the amount of ice and things below, so the effective temperature is T minus Tg. Okay? This is going on here, and this is how C2 goes. And this here depends in some way of the amount of biology. So this is B is sort of the size of the biomass of the planet here. So the more biomass you have here, the less CO2 in the atmosphere. Okay. Now, how do we model the biosphere? Well, the simplest thing to do is the simplest biological model you can say would just be like a logistic growth, right? Birth rates and death rates and things like that. So you have a logistic term here, but you have a factor here that would depend on the temperature. It will only grow when temperature is optimal, and of course there might be a depth rate that's independent. So it's just a specification of this optimal temperature here that would give you to go through biology. So I just modeled this as a simple Gaussian here, where this is the optimal temperature. If the temperature gets too low, biology will be less. If the temperature gets too large, biology will be less. This is as I see it, the simplest model that you can come up with for the connection between surface temperature and biology. Now, if you didn't solve it, and that's not very hard to do, what happens is that if you take you plug these two terms, now for simplicity I'll just take this one to be a constant all the way through. Of course, you can do all kinds of things, and what people also do is look at the albedo as a function of the biology itself, because the forest is darker, it absorbs more than a desert, so of course you could do that, but here it's just taken as a constant. And then you have this greenhouse outgoing radiation, and it is now changed from the abiotic to a biotic state here. Now, already this, so you can almost recognize this one just going on top of that one here. Now what you see here is that, as in the abiotic case, you have in the biotic case one stable climate situation. But if this one here, the incoming radiation, is shifted up here, okay, suddenly you get the same situation of a stable and unstable and a stable fixed point here. So you can get a sort of two-stage situation, a lifeless planet and a life-lit planet, where life itself generates its habitability. It's sort of the message that in this case here, habitability is made by the biology. So if we start out here, we have to penetrate a barrier to get over here. Life has to cool the planet enough to be able to be there.
What is on the y-axis?
On the y-axis here?
Yeah.
This one here is just this function u.
Yeah.
Right?
But what's the unit on the y-axis?
The units on this one here, well, whatever the units are, this one has no unit, so I guess this one has no unit.
Because it says 1, 2, 3 on the left one, and then 100, 200, 300.
Oh, this one here is a different axis, right? This is the radiation, this term and that term here. So this would be, in this case you have something like watt. The usual unit would be watt per square meter, right? Incoming watts per square meter, right? How much to radiate and how much to get in. Yeah. This one, and here's temperature. I'm sorry, pretty poorly done. So, if we then look at the equilibrium temperature as a function of solar luminosity, so this one is really what should be compared to the one for the basic world, we will sort of toy model. This has some sort of naive realism to it. But you see the surface temperature in an abiotic world will increase like that with solar luminosity here. So if I have a biotic world, I will have some sort of stabilization here, in the sense that the slope of this one is less, and up here you really have the sort of bimodal situation here. This is sort of a way of looking at it.
But now the x-axis should be your energy input.
This is energy input. It is solar luminosity.
But I thought the units were like a few hundred.
This is the solar luminosity. This is present day solar luminosity. This is 2 times present day solar luminosity. This is 0.6 of that. I mean, so this is and this is the surface temperature we have up here, and it's about 350. Surface temperature. Of course, it's in the ballpark of what you see today. Of course, in such a naive model, we would think that So the question is, I mean, the discussion is, of course, now what is this is probably pretty close to what's happened on Earth, in the sense that we know biology is influencing the climate, but it's doing it through the oxygen and the lack of carbon dioxide in the atmosphere. Okay. The question is, how much is this just a non-dynamical following of a given history, and how much is this really a dynamical system that gives a sort of hysteresis, which is hysteresis is, of course, the idea that biology is able to compensate for whatever changes in external forces you have. That's sort of what divides the discussions in the community, and this more Gaia type of people are looking for sort of principle, like, what do we look for?
To make it clear, so the abiotic temperature is like 50 centigrades above the biotic temperature.
Yes. That's about right. Even if you look at Venus now, it has a temperature which is something like 700 Kelvin, 400 degrees on the surface. It's a little different. And of course, I mean, in this case, of course, you would need really to know the details. I mean, you could also imagine that we would have stayed in snowball Earth, which means that then the planet would be much more like Mars. Mars is something like -80 Celsius. Even though you could still have positive degrees on Mars, in the summer. So it's, of course, just in the ballpark. But the message is, of course, that it might be that that life is really governing what's going on in the surface layer of the planet. And some ideas are that maybe one should look at the ability of keeping the temperature low. So the question is whether it's just running what I was saying. Is it such that changing the solar luminosity here really so that biology really makes it more stable than the biotic situation there? The other thing is looking at the entropy and so on, but I think I should go too much into this now. Just state again that I think that the biology of the planet is really crucial in order to understand the climate changes on the geological timescales, and that should probably make us think about more realistic climate models for the type of changes we have. Now, this is sort of in one end of the spectrum. The other end of the spectrum, you have the climate models that are sort of the basis of the IPCC reports and so on. And in these models, we also built in the effect of biology, of plant cover, of the hydrological cycle, depending on plant and all these things. The problem is that they have a complexity that is so huge that they're so controlled in a way that they can never experience the changes we've seen on the planet. Say if you turn the sun up and down in one of these models, you'll never see a stability that really looks like what you see on the geological report. In sort of intermediate things, we know that we can have different types of stable states in terms of a green planet or desert planet, and also violet planet. So I think I should stop here.
Yep, thanks.